Welcome guys to a new LS-DYNA tutorial, and in today's video we're gonna do a 3-point bending test. Don't worry about the simulation that you are seeing right now. We're gonna do a 3-point bending test of a sandwich structure, and the core of that sandwich will be what we call it EPS form, expanded polystyrene form, which is what you see in the simulation right now. Is a car impacting a block or a car crushing a block of the EPS form. The simulation that you're seeing right now, it's based on my final year project, and I also don't know why I made this simulation. Okay, so without wasting any time, let's go and make our simulation of the 3-point bending test. So first we make the core of our sandwich structure. So the core of course will be made of solids. Shape measure, we go to mesh, shape measure, and we have a box, and the length will be 1500. The width will be 75 and the height will be 50. The number of elements here, let's say 60, and in Y it's 3, and in Z let's say it's 5. And then I call it EPS form. EPS form is type of form that you will find in the packaging when you buy a new phone or anything. The packaging is made out of the expanded polystyrene form, or the common name for it is styrofoam. So here we have our specimen. We have our core. Now we're gonna make the upper face and the lower face. Of course you can make it using shell element, but for this tutorial I'm going to make it with split element. So if I want to see the thickness of one layer is 10 mm, okay, fine. So here I want to translate in the Z direction. Distance is 10, and then I click by element, click here. I need to click I need to make a copy, so I need to look the right side, and again I click by element, make an area. Okay, now this part, let's say it's part number 2, and then I move up. Now I have our upper layer, our upper face of this structure, sandwich structure. Okay, similarly I want to make the lower layer, so I can go to front view, is easier. Click on this guy, then I want to make it a different part, so I put 3 here and I copy the element, translate minus. Okay, now we are done, but I want to change it a little bit, okay, because I want to make this thickness more thinner. So I go to scale, make it, let's say 1.1. this is a scale factor, scale in Z, scale by part, and the origin I click on any node here, then I scale minus, make it smaller. Okay, let me see how many times. 1 2 3 4 5 6 7. Okay, this is acceptable. Now for the lower part, I click the origin. Always remember to click the origin and then scale 1 2 3 4 5 6 7. Okay, why I make this one and this one different part? Because I want to assign different material properties. Let's say I want to make the lower one made of steel and the upper one made out of aluminum. If you have the upper and the lower made from same material, which is most of the cases, then you can just keep them as one part. So this one will be blue or green. They will be in the same color. Okay, now we want to fix the upper and the lower layer to the core. The way I made the layers doesn't make them fix automatically, because I translate and I copy the element. So if I want to fix them together, I want to attach this one, layer 1 to the core and the lower layer to the core. There are few ways. The easiest way is you just click here on duplicate node and show duplicate nodes. Okay, so here if you click on merge duplicate nodes, it will fix the nodes, so it will be fixed at each node. But what if the nodes are not in line with each other? What if, let's say, the mesh of the core and the mesh of the layers are not aligning? So in that case, one of the ways that you can use is using the contact type nodes to surface. So before I proceed, I want to mention that using either of these two methods, using the duplicate nodes or the type node to surface, will make a perfect bonding between the parts, meaning there will be no delamination or no separation between the parts, except if the element themselves eroded or failed. So to make the node to surface contact, first I need to define the nodes. I need to define the node set. So create identity, and then I go to set of node, then create, and then here say EPS upper node set, and click by element, apply. Then similarly the lower part, EPS lower node set, and click by element, propagate, and then accept. Okay, now I need to define the surface that will be attached to this node set. So I click on number 2 and 3, part 2 and 3, then I go to segment, and here this one will be front face lower surface. This one, let's say I call it the front face. So I click by element, propagate, and this is the segment, then apply. Then again I go down here, click, I name it lower face or back face. I'll call it back plate, easier. Upper surface, apply. Okay. Now here I just hide this one and then hide this one, show everything. Okay, go to the model keyboard manager, click on all, and then contact, then you go to tie node to surface. Okay, if you want the delimitation or the separation, you can use tie break node to surface, or you can use the cohesive elements, but I will cover those two topics maybe in future tutorials. So now we just go with the simple cases of tie node to surface, contact ties node to surface, new ID, then upper layer and foam. Okay, so tie nodes to surface, so our slave should be always node, which is number 4, node set. So EPS upper node set, and then the lower face of the upper plate, accept. Okay, then new ID, then lower layer and form. Here the lower node set, and here we have the lower plate, the upper face of the lower plate, then accept. Okay, so now I want to define the material properties. Okay, so the material properties, I will start with the easy things first. So for the plates, they will be made out of metals. So that's the easier way, the easiest part. So I will go to material number 18. I make it, let's say, number 2, and say this one may be made out of aluminum, and I will go and copy or steal from this database. This is from Parmintal's engineering website, and I may have mentioned this website many times before. So I will take say steel, any type of, let's say, aluminum. Okay, this is small, make it bigger. Okay, just take any one of them. Let's copy here, copy, and then there's this one, so it will be easier for you. So this is the aluminum, the name, and then we have the properties here. We are using kilogram millimeter as our unit system, so the strength of the model should be in megapascal. Poisson's ratio, sorry, copy here, and then you have K and N. Failure, okay, we can introduce the failure as well. Okay, why I made this ID 2? Because I want to assign this one to this one, which is part number 2. You can put any number, but as a good practice, I prefer the material ID to be the same ID as the part ID. So if this is part number 2, the material ID also will be number 2. Okay, now I add 3 for the lower one. Let's say I want it to be made out of steel or iron or whatever. Okay, you have the steel, just come in front of my face, copy, oh no, not here, copy, and then go paste here. Okay, go up and see the name, the title or the name. Of course, it's not important, it's just a good practice. Then you copy this one, you paste it here. This is the density, and this is the modulus E. This is Poisson's ratio. This is K and N, which is the hardening parameters, hardening exponent N. The failure will happen at this point, then accept. So we have this type of aluminum for the upper layer and this steel for the lower layer, for the lower plate. I better be smart this time and Control S. Here 3 point bending, 3 point bending. Okay, then accept. Okay, so we stop at defining the material. We define the material of the upper and lower plate, which was very easy. We covered that before. Now we want to define the material of the foam. There are few material models that are used for modeling the foam behavior. One of them is 26 honeycomb. This one is quite common. If you have any file of a complete vehicle, then they will use this type of material to model the radiator. But in today's video, I will use material 063, which is crushable foam. So let's say put material number 1. Okay, this one EPS form. In the material properties for this guy, the density is 1.275 E minus 8. This is the density. The Young modulus 0.00206. Poisson's ratio is 0. Cut-off tensile strength is 0.1 E minus 3, and the damping coefficient is 0.5. Can accept. We have one more thing to define here, which is the load curve. Okay, so we go to all, go to define curve, then new ID. This is the stress strain curve, and then I import the file. I have this CSV file, I import it, then accept. And you plot, you can see this is the curve. Okay, this is actually an experimental curve that I got it from the experimental work, and the actual curve is only until strain equal to 0.8. Okay, from 0.8 until 1, this portion I added this one like using interpolation, because if the curve is only until 0.8, then there is a high possibility of what we call it a negative error problem. So now we have the curve defined. We link it to the material model. So here I put number 1, accept. Okay, so these material properties of the EPS form and the curve is actually taken from here. This is a paper published in after my graduation, my degree, and this is the curve that we did. This is the experiment that we did, and we got the curve here, the experimental curve. And the material properties that I've mentioned just now are taken from here. Okay, so we go back to our simulation. Now we just almost completed defining our sandwich structure. We need to define the section. Go to all, then section, solid. Here we have EPS section number 1, accept. Now the plate section. Okay, for the plate section I will use number 2, which is fully integrated solid element. Okay, EPS section number 1, or the default. Okay, new ID, and then plate section. So again, I was saying for the plate section I'm using element formulation number 2, which is fully integrated element. Why is that? Because here we're gonna do a 3-point bending test. So this specimen will bend, and there will be a moment in the y direction. And when you are using solid element and it is bending a problem, you have 2 options. Either you make the thickness here, you can increase the number of element here, or you can increase the element formulation, or using a higher order element. Of course, if you just go with the standard, then the simulation will run fine, but your simulation will not be accurate. So to sum up, what I was trying to say. If you're using solid element for bending problems, then you better use higher order element. So fully integrated solid element if you are using solid element. Or if you want to use the default, then you need to increase the element through the thickness. So instead of having one element here per thickness, you may have 2 or 3. Okay, so now I go back to part and I link those guys. So the EPS form section is 1, material is 1, this one we call it aluminum or upper plate, section is 2, and it's aluminum except, and then lower plate, and here is this one plate section, and then steel. Okay, now we are done with making our specimen. Now we need to make the setup of the 3-point bending test. So I want to make a cylinder up here and another 1 and 2 down there. So I go to shape, go and I make a solid cylinder and try to create. I don't know where did it go, but here I can click on the position. Let's say my position, I want it to be here. Okay, create position by node, click on this node, done. And if you accept or if you create, you can see it's going, the cylinder is going this direction. So actually you need to change it. So the direction you change from here. So it should be in the Y direction. The radius I will make it 60, and the length is let's say 90. Now you can see this is our cylinder. Or the length I need to change it 80. Okay. And the number of element here I want to make it 80 as well. Alright, so now I click on, I will name it first punch or whatever you name it, then click on accept. Right here I made a solid cylinder. Of course the tools, the punch and the support will be rigid, so you can actually make them as shell as well, but I want to make it solid because I want to show how to make this one from a solid and make it a hollow. So you go to element tools, go to element editing, again sorry not element editing, delete the part, and then click by element, propagate, increase the degree, then you right click on the surface and then you delete. Now we have a solid tube. So this is a simple way how to make a solid tube. Alright, so enough with that. Now we move this to the center. So in the X I have 750, move by part, move positive. Now I move in the Z and then make it up, click on right view. Okay, it's almost touching, so just make it 1 mm higher, then accept. Can move it also back in the Y direction, click on the front view. Yeah, so like this is perfect. Okay, now I want to make the support down there. So how can I do that? I move by Z and make a copy of this. So this one will be part number 5. Then I copy, make a new part, and it's part number 5. I click by part, Now I move in Z negative. Okay, click on the front view, make it close enough. Okay, done. Now I need to make another copy of this one and then move them to the side, one to this side, one to the other side. So here I move by Z. Okay, no, move in X direction by part 750. I don't make any copy. I move to the far end first, and then I want to create a copy and move them to this one. I mean create a copy in the other end. So 150 and negative, the positive, and then we have it. Now I just want to shift this one a bit, let's say 100. Now I cannot click by part, I mean I can click by part, but this one will be selected as well. So I just click by element and propagate. So don't want to make a copy. I need to select the other, okay, the inside and the outside. Okay, if I click on the right view, you can see here this is okay, quite acceptable. So the other end also I use the same thing, I move, and this one will be negative. Oops, again I made the same mistake. Okay, now we have the setting of the 3-point bending and nothing is touching. It's almost touching, is fine. Okay, now control save. Yes. Alright, so now I define the rigid materials for the punch and the support. Here I click on all, collapse, then material number 20, which is the rigid material. Then here I call it punch. This one, let's say this is steel 200 0.3. Okay, this one is fixed in Y and X. Okay, so constraint in Y and X. So this one number 4. It's only allowed to move in Z, and the constraint 2, constraint 7, meaning cannot rotate. Then I accept. Then new ID, set first. I change this one, support, and then what I do, I change this one also to 7, because the support cannot move and cannot rotate in any of the degree of freedom. The section should be the same section, solid section, doesn't matter because it's like rigid parts. So here this is the punch section, and this is the punch number 4. Okay, this one doesn't matter as long as we choose a solid section, and this one is a punch, a rigid material model which is allowed to move in Z. Accept, and this is the support. And then section, same, this one should be 5 support, because this is a rigid material model which are not allowed to move or translate or rotate. Accept. Done here first, then accept. Now we need to define the contact. Okay, so contact here again, type node to surface, I have to click on all, and automatic surface to surface. This is the standard one. UID, so punch to upper plate. number 3 and number 3. This is I will say the punch will hit the upper plate, except wait a bit. Now new ID, then say lower plate to supports. So the lower plate is this one and the support is number 5, and accept. Wait again, it will take some time. Okay, so right now control and save. Okay, so now we have defined the contact. We need to define the displacement of this punch. So you go to define and curve, and before that I want to see the displacement. Say from here to here is 70. Okay, so I go to curve, add displacement. Okay, when time is 0, displacement is 0, insert, and when time is 100, displacement, let's say 140, insert, and then the curve will be, the displacement will remain there for 10 seconds or 10 milliseconds. Okay, so we have till here until here. Now I go to boundary, prescribe motion rigid, new ID. This is the punch, and degree of freedom in Z, so it should be 3, and then load curve displacement, and here it is, punch displacement. But remember that our curve is positive, so if things are like this now, then it will go up. So here I will multiply by -1 and accept. So I'm making number 1, accept. Okay, so now I save this one. Right now there should not be any problem. I believe the model will run fine, but if you remember what we did here, we extended the curve of the stress strain so that we avoid what we call a negative volume problem, right? So the following things that I'm going to do is actually some of the other measures to combat or to prevent the negative volume error in the solid element, in the soft solid element. Another step that you need or you can do to fight the negative volume is to create a part set here by part, and here you put 0.1, here you put 2, and this you can say form part set, then apply. And then using that part set you define a contact, you go to contact, and then we call it contact interior, then accept. Another thing that you can do is you define hourglass. So click on the hourglass, form hourglass. This is if your case is high velocity. If it is high velocity, then you can make it the hourglass identity number 2 or 3. Okay, 3, and the coefficient 0.1, accept. If it is a low velocity problem, then you might want to use IHQ equal to 6. Okay, we define the hourglass. Now we link the hourglass to the material, to the part, sorry, and here is hourglass one, accept. Okay, now if you remember, here in the definition of the solids, we define this plastic failure strain for element deletion, meaning the metals, the plates will be deleted if the stress and strain, if the strain is too high. But what about the foam? Right now we did not define any failure for the foam elements. So to define that, we can use add erosion here. Add erosion. The title, leave it empty. Material, we want the erosion for material number 1, which is the foam. And here, these all the failure criteria that you can use. And in our case, we have 2 failure criteria, which is the minimum pressure minus 3.75, E minus 5, and then maximum principal strain 0.15. So these 2 criteria must be fulfilled together at the same time for the element to be deleted. So here, number of failure condition should be 2, meaning if one is satisfied and the other is not satisfied, then element still will not be deleted. And number of integration points, if you remember, for the EPS, we are just using the default element type, which is 1 point element, 1 point integration element. All right. Now we need to use this exclusion number. Why? What is this for? Actually, let's say if I put this is 1, 2, 3, then here I put 1, 2, 3. Okay, if this number is the same as this number, then this failure criteria will be ignored. So the software will not look for the maximum pressure as the failure criteria, because I'm using the number 1, 2, 3, and the number 1, 2, 3, I put it here as the exclusion number. So this one, minimum principal strain also I don't want, the effective strain I don't want, volumetric strain I don't want, and the same with the other failure criteria set. So now we have defined the failure in the EPS form, but this for this bending, I'm not sure whether there will be a failure or not. So back to my paper, this is actually the behavior of the foam without introducing the shear or without introducing the failure, which is not real. Okay, because the styrofoam, it doesn't have this sort of elasticity. This is more like rubber. That's why we introduced the failure. Okay, so one last thing is you go to control and contact. Here we have a lot of things. You just change this one in mass to number 1. This is a practice if you have defined artificial failure criteria like the add erosion. Okay, and what does this do is, like, the element that have been eroded, the nodes will be still active in contact. It might make the problem a bit longer, but it should give more accurate result. Alright, so now we want to ask for the output. Or before that, I need to control the termination time. I've not defined it yet. Control termination. Up here is 100 milliseconds. Accept. Of course, 100 milliseconds is very fast for a 3-point bending. So you can calculate the rate and the time according to your rate, the displacement rate in your testing experiment test. termination done. Now we ask for the database. Where is it? D3 plot. We have, let's say, 0.1 or 0.5. Accept. Done. And then I save this one first. That's the options. Okay, this ASCII option always take time. This is 0.1, and I just want one thing, which is the boundary condition forces. Enter, accept, and then control save. Now I run this and see if everything works fine. Is this the one? Yeah. I'll maximize everything so it doesn't take time. Okay, error. Load curve 1 has a vertical slope. So here, go to model, define curve. The vertical slope is somewhere here, I think, in the start. So these are the problematic points, so I just can delete them. There are many of them. Okay. And then I think I can delete as well when it is negative. And accept. And save. Then you rerun again. It will take 8 minutes. I believe it should be faster. Oh, there is element deletion. There is some failure of the element. That was unexpected. So we got the results now. It finished running in 2 minutes and 39 seconds. We go to the keyword manager. I open the last result. Let's see what do we have here. The displacement is too much. Okay. So there is the failure of the element on the form, but we did not have any error termination. That's the good part. So this is the compression of the form. Alright, before I want to modify this one first, but before that let me try to show some few things. We go to ASCII options, boundary, and click on load, and click on this one. This represents the force of this guy. Okay, so now you click on the Z force and you plot, and this is actually the force. Okay, and since you have the force, you know the span of this one, you can find the moment, and from there you can find sigma for bending, sigma MC over I. So you can have the curve and you can compare to your experimental work. Okay, so I close this one. I need to modify this. Here is the mistake. VAD, this one should actually be equal to number 2, because our curve is a displacement curve, it's not a velocity curve. Okay, so putting that equal to 2. So I save this and then I run again. So now we have the simulation results in 2 minutes, and I open the file. I open the results. Now you can see this is the 3-point bending of the form. As you can see, we have a bit of hourglass here. This is because of the hourglass mode, because I think this is still considered as low velocity. So what you can do, actually, you can change the hourglass control from 3 to number 6. Part. Click on this velocity, not displacement, the velocity. Yeah, and the velocity is actually only minus 1.4. So this is a low velocity problem. So the hourglass, you can change it from 2 to 3 to avoid this hourglass modes. And you can see there is a perfect bonding between the layers, between the core and the plates. You can see the nodes still are the same, they're not sliding. So that's meaning the modeling of the perfect bonding between the core and the plates are working. Okay, so now we will try to change the hourglass and see what happens. So here, as I said, this is the displacement curve, not the velocity. Hourglass, make it hourglass number 6, then accept, then save. We close this and this and this, and then you rerun. So we got the results now after the modification, and I open it here. I already opened it. So you can see here is the bending, and the hourglass deformation modes are not visible as in the previous example. So here is with the not updated hourglass. This is hourglass type number 3, and this is the hourglass type number 6. Okay, actually you can see the difference, this one and this one. So this is a low velocity problem, so you use hourglass type equal to 6. So I think it has been a very long tutorial, so I will leave it here. I will stop here, and I will mention few things. First, about the contact between the support and the foam. You need to update and make it surface to surface, and you define the segment of the foam, all the segments, or you can use automatic node to surface contact also. It will work, but I found out that surface to surface with define the inside segment will work better than node to surface. So I will leave that one as for you to practice. You can check the simulation here. I've mentioned as many details as I can. So if you can get the failure and get a result similar to this one, which what I got here, then and the displacement also similar to the experimental, then you are doing a very good job. So I think yeah, that's all for today. I hope you learned something in this very long video, and don't forget to like and subscribe, and stay tuned for the coming tutorials. Thank you and see you next time. Then the automatic surface to surface, we need to do some modification. So here punch to upper plate, so it will be punch to form. Okay, so the easy way, I just change this one from to form and accept. But by doing so, I might not get a good result, because defining a surface to surface contact will only define this segment to this outer segment. So the contact will not be defined between this one and the layers inside. So what happened if this layer got deleted? Then the thing will not know the inside layers of the form. So to fight that problem, I defined contact between the surface and the segment set. So here a new entity, I want to define the segment of the form, new entity, and then here I just go create, say form segments, then click by part and then apply. Alright, and then accept here, and for the second one also I do the same. So this one will be segment and this one will be form segment.